Hi, and welcome to Control Talks. In this video, I'm going to give a small introduction to mathematical systems modeling. As control engineers, it is crucial to describe your system so you can control it. We cannot make control if we don't understand the process. To describe and control complex systems, we do it mathematically. And because the systems under consideration are dynamic in nature, the descriptive equations are usually differential equations. A differential equation is an equation that contains one or more functions with these derivatives with respect to a single independent variable, in this case, time. This is the notation for the derivatives with respect to time. In this case, we have a second-order ordinary differential equation. We call this the mathematical model of the system. This allows us to know the position of the mass, in this case, y of t, by solving the differential equation. A differential equation is great for solving for the response of a system, but it doesn't lend itself very well to analysis and manipulation. And this is something that we absolutely want to do as control engineers. The whole point to analyze how the system naturally behaves is for then manipulate it so it behaves the way we want to. Luckily, there are other ways to represent a mathematical model which makes the controls engineer's job easier. The two most popular representations and the two that we will cover in this course are the state space representation and transfer functions. We are not covering state space representation right now. For now, we will be working with transfer functions. If you haven't already noticed, transfer functions are a Laplace domain representation of your system. Yes, we will need Laplace domain knowledge for this course. Before going through the definition of transfer function, let's go into some concepts first. Since we are going to use the Laplace transform, the systems we are going to analyze under this course are going to be linear and time invariant systems. First, we need to learn what an LTI system is and review a small amount of linear theory. I'm going to represent an LTI system with the linear operator G. This notation provides a linear mapping between the input u of t and the output y of t. For a system to be linear, it should have the following properties. The first one is the principle of superposition, also called additivity. This principle says that if you sum two separate inputs together, the response to a linear system will be the sum outputs of each individual input. Or in other words, g of u1 plus g of u2 is going to be equal to g of u1 plus u2. The other property of linear systems is homogeneity. It means that if you scale the input u of t by a factor of 2, then the output y of t will also be scaled by 2. This means that g of ax is going to be equal to a g of x. Linearity is only the first part of an LTI system. The second part, time invariance, refers to a system behaving the same regardless of when in time the action takes place. Given y of t equal to g of u of t, if we shift the input u of t by a fixed time t, then the output y of t is also shifted by that fixed time. This is called time invariance. We are getting close to define what a transfer function is. We already got through the definition of LTI system, but we still need to talk about the Laplace transform. The Laplace transform of a function in time, let's say x of t, is the integral from 0 to infinity of x of t e to the minus st dt. We call this capital X of s. Now, s is a complex variable and is defined as s equal to sigma plus j omega, where j is a complex number. If we substitute the complex variable s in the definition, you can see now that the equation e to the minus st is really just an exponential function with a real exponent number multiplied by an exponential function with an imaginary exponent. Exponential functions that have imaginary exponents produce two-dimensional sinusoids through Euler's formula. This means that the complex variable s contains values for two dimensions. One dimension that describes the frequency of a cosine or sine wave, and the second dimension that describes the exponential term. Now, how this is important? Well, because solutions of differential equations must be either exponential or sinusoids. So this is how the Laplace transform is an important tool to obtain the solution of differential equation and ends to help us represent physical models. Now I think we are ready for the definition of the transfer function. The transfer function of a linear system is defined as the ratio of the Laplace transform of the output variable to the Laplace transform of the input variable, with all initial conditions assumed to be zero. From the definition, I will emphasize three things. The first one is that only applies to linear systems. The second one is that a transfer function tells me a relationship between the output and the input. It means that for a given input, I can be able to know the behavior of the output. And the third thing is that all the initial conditions need to be zero. Now, let's go back to our mass spring damper example. This system model is a perfect candidate to convert into a transfer function. It's linear, time invariant, and there is a single input fu and a single output y of t. Solving differential equations is not easy, but we can take the Laplace transform of the entire differential equation one term at a time and solve for the response of y of t under an input fu of t in the S domain directly. A great thing about working with linear systems is that usually we don't have to perform the Laplace transform integration by hand. The Laplace transform for most of the terms that you will come across in this type of models have been solved many times before and collected into tables or into theorems. One of the most useful theorems that we'll be using is the Laplace transform of a derivative, which it is as follows. Here, x of 0 are the initial conditions of the system. But remember that for a transfer function, we must consider initial conditions equal to 0. If we consider that, the Laplace transform of the first derivative becomes s x of s. And for the second derivative becomes s squared x of s. So with this in mind, we can take the Laplace transform of our model equation as m s squared y of s plus c s y of s plus k y of s equal to fu of s. This is the Laplace transform of this differential equation. Now, how do we find the transfer function of this Laplace equation? Well, the definition says that is defined by the ratio of the Laplace transform of the output to the Laplace transform of the input. So we can factorize y of s and divide everything by the input. G of s is the transfer function of our model. Let's dwell on something for just a bit. The transfer function represents the dynamics of the mass spring damper system, and we can use this representation to predict how the mass will move when subjected to arbitrary forces. Let's just consider how the mass will move when subjected to a force Fu like the one shown in the animation. This type of input is called impulse response. In this case, it can be described as just as an instantaneous punch over the mass. Don't worry, we are going to talk more about the different kinds of inputs later. The way the position of the mass y of s is moved is called the transient response. So we have learned that the transfer function of a system will help us to represent the dynamic response of an output with respect to an input, assuming initial conditions equal to 0. Mathematically, we can find the transient response of y of s for whatever input by multiplying the Laplace transform of the input with its transfer function, and then perform the inverse Laplace transform on y of s. Later, we're going to learn how to make this in programs such as MATLAB or using Python.